For this lesson, we're going to talk about set notation. Now, talking about sets, we really want to first start talking about the number system, the real number system. There are imaginary numbers that you'll run into when you get to Algebra 2, but for Algebra 1, we're really just talking about the real number system. And in that number system, we classify certain numbers as being in a set. So first I'm going to show you how we classify those numbers and what those classes mean. And then I'm going to translate that to sets and how we use set notation to show certain ranges of numbers, which kind of blends right into how we work with inequalities when we have to show a range of solutions. Now you should have this page right here called the real number system. We're going to end up taping this to the left side of your entry for set notation. But let's talk about what this means. So this is a breakdown of the real number system. And we have these different sets of real numbers and where they fit. There's what's called the natural numbers, whole numbers, integers, rational numbers, and then over here kind of off to the right is irrational numbers. So you notice how these boxes are inside of a box and inside of a box and inside of a box. That's because a natural number is a whole number, which is an integer, which is a rational number. A whole number is an integer, which is a rational number, right? So a lot of these are kind of intertwined, and all of these are all considered rational numbers. So it's kind of like a set within a set. And as we start to look at what numbers these are talking about, you'll start to understand why the irrational numbers aren't here. So when we talk about natural numbers, those are counting numbers. So we're kind of really way back, right, when we first started talking about numbers, like centuries ago. The reason numbers came up is because we had to figure out, well, how many of something do we have, right? Do you have one sheep? Do you have two sheep? Three sheep, right? And that had a lot to do with trading. Am I going to trade this one sheep for these two chickens, that kind of stuff. So the natural numbers are also called counting numbers because that's what we use to count. So, for example, 1, 2, 3, 4, right? Those are all natural numbers. 5, 6, 7, 8, right? So then time went on, okay? So as the history of numbers progressed, they started realizing that they needed something to represent the absence of having something, right? So not counting, but what happens if you don't have anything to count? So they came up with the number 0. So the whole numbers are 0, 1, 2, 3, 4, 5, 6, 7, right? It's the natural numbers plus 0. And that was that went on for a while, right? There was 0, like you don't have anything. You have 1, you have 2 of something, 3 of something. And they had to figure out now what happens if you run into, like, not just the absence of something, but what if you're missing one thing, or you're missing 2 things, or 3 things. And so we had to include what's called integers now. So integers are these numbers, but also their opposites. So -1, right? -2, -3, -4. Integers are the whole numbers, right, plus their opposites. And then, as the history of numbers progressed, they had to think, well, what happens if I don't exactly have 1 of something, or 2 of something, or 3 of something? How can I represent that? And that's represented by, as you know, a fraction, right? A fraction is a part of a whole. So rational numbers are those fractions, like 1/2, right? 2/3, -6/4, right? Those are all rational numbers. Rational numbers can also be decimals. 1.5. Right? That's a rational number because it's 1.5, which can be written as a fraction. So as long as you can write a number as a fraction, it's going to be rational. This 2, right, is a rational number because I can write it as 2 over 1. Okay. Now, separately, right, we have what's called irrational numbers. So irrational numbers came up when we tried to solve math problems. Okay, we needed something to represent a situation that occurred, but we didn't have a specific number for. So for example, pi. There's no specific number for pi. Right? It's 3.14159 and it keeps going. But we don't have a specific number for it, so we represent it as a symbol, right? A variable, and it's called irrational because we can't represent it as a fraction. Another one, the square root of 2. The square root of 2 doesn't have a perfect square root. That is an irrational number because that decimal never stops. Square root of 3 is also irrational. Right? Square root of 4, well, the square root of 4 is actually 2. So that's a rational number. But the square root of 5, right? So those are all called irrational numbers because we can't represent them as a fraction. So that's called the real number system. Okay. And I also want to show you a way we represent these different types of numbers. So in math, when we're talking about the natural numbers, we often use this symbol, and it's an N for natural, but that N has an extra line in the middle. Okay. Whole numbers are sometimes represented with a W that has an extra on the side. Okay. Integers are represented with a Z that has a line through the middle, right? An extra line there. Okay. The rational numbers are represented with a Q that has a line right there. Okay. Irrational numbers, there is a way that we represent irrational numbers as a system, and it's called, a different name for them is algebraic rational numbers. And so that symbol is an A with an R. Okay, the R stands for this real number system, because this symbol is for the whole symbol, the whole number system we're talking about is the real number system. So it's important to have these symbols learned so that when we talk about ranges of solutions, you can say, oh, well, x is 3, that's a natural number. Or x can be any integer, right? So we don't have to say integer, we can use this symbol. And that's going to be important when we start talking about sets, which we're about to move on to. So you're going to tape this real number system to the left side of this entry so that we can reference it when we talk about sets. So you can pause and go ahead and tape that in there. So when we talk about set notation, we have to first define what a set is. So a set is a collection of distinct elements, and sets can be represented in two different ways. So a set is just a collection of distinct elements. Distinct means it's not repeated. So this is a set. Elements in there would be 1, 2, 3, 4, right? The rational numbers, those are a set. Elements in there would be -4, -3, 1.5, 3, 0, right? Those are all elements in there. So when we talk about a set being a collection of elements, okay, elements are just what is in the set. Okay. And now we're going to talk about the two different ways they can be represented. So there's called roster form, and that's when you make these curly braces and you list off all of the elements that are in there. That's called roster form. Kind of like a class roster, where the teacher has a list of names. Every name would be an element in the class set. Kind of think of it that way. So each of these are elements of this set that I just made. So curly braces, as you start going through your math class, you're going to get more used to making these. Kind of think of it as an S with a larger upside and then a backwards S. Okay. And you can just keep practicing and practicing and practicing. I was a super nerd when I was in school, so instead of doodling, I would just keep trying to make curly braces. That's how I got pretty good at it. So you're more than welcome to try that. The second way to represent a roster, to represent a set, is called set builder notation. So this doesn't list out all of the elements. Okay, what this does, it describes the properties that an element must have to be in the set. Okay, so for example, we would write it this way: curly brace and then an X. So this represents numbers X such that X is an element of the natural numbers and X is greater than or equal to 6. Okay, so X is a natural number, and that's where this symbol comes into play. Okay, so this is, again, we can read this as values of X such that X is an element. That's what this kind of E means, element of the natural numbers. That means it's 1, 2, 3, 4, 5, right? But also that X is greater than or equal to 6. So if I were to switch this into roster form, and I can just kind of do this here, that would be 6, 7, 8, 9, right? These are all natural numbers. They're greater than or equal to 6. But I'd have to keep going on and on and on and on and on, right? If I wanted to list out all of them, it would take me forever. So that's why set builder notation is really useful, because we're describing the set and what elements will be in there without actually having to list them all out. And that's going to be really helpful when we start showing our solutions and range of solutions as a set instead of just a number. Alright, so now we're going to use set notation as an example when we solve an inequality. So you've started already solving multi-step inequalities, so we're just going to go through the process. We have negative 5x plus 7 is less than or equal to 17. So let's solve that inequality. First, I'm going to subtract 7 from both sides. That gives me negative 5x is less than or equal to 10. Then I would divide by negative 5, and I'd get x is now greater than or equal to negative 2. Remember that golden rule where we have to flip the inequality symbol. Now, to show that as a set, okay, I would write my curly braces, and I'd say that x, or say its values of x, such that x is greater than or equal to negative 2, and then end my curly braces. So that is saying that the solutions are all of the numbers that would be in this set. Now, I'm going to be okay with this answer, but if it asks you to put it in a set, then I want you to understand what this answer represents. Okay? So these mean the same thing, but as you start getting into higher level math classes, you're going to be going from here to here. Okay, so familiarize yourself with this way of answering problems that have a range of solutions, like inequalities do.